Okay, so here one of the things that we need to look at is when we're talking about nuclear reactors is the chain reaction. So what is a chain reaction? When a nucleus splits into two smaller parts, which is called fission reaction, splitting reaction, it produces two new smaller daughter nuclei and a number of neutrons are released. These neutrons go on to join with other nuclei and cause those other nuclei to go through a fission reaction. What we have is a chain reaction, a reaction of one nuclei that leads to a reaction of another one, which leads to a reaction of another one. Okay, so reaction happens in a chain. That's what it happened. So first, a nucleus absorbs a neutron, becomes very, it sounds stable, but as soon as it absorbs that neutron, it will then fracture and split into two smaller parts. Here we've had 3 neutrons released. Okay, these 3 neutrons could go on to be absorbed by 3 more nuclei, and those 3 nuclei could then split. So we started off with 1 splitting nuclei, then we had 3, now we've got 9, and so on. And what could happen is we start off with very few nuclei splitting, and very quickly we get lots of nuclei splitting. And this is what we call an uncontrolled chain reaction, because it gets the reaction increases and increases and increases. Okay, so starting off with 1, and then after just 1 second stage, third stage, we've got 9 nuclei splitting. So this can release an enormous amount of energy, because when the nuclei split, some of the energy that's locked away in the nucleus is released as thermal energy, because the daughter nuclei, they spring apart, or when the nuclei splits, they shoot off in different directions, collide with neighbouring atoms, and cause those neighbouring atoms to vibrate. Hence, the nuclear energy turns into thermal energy. So, if a chain reaction is uncontrolled, this energy that's released as heat energy will build up very quickly. Okay, to keep the output steady, we need to control the reaction. So how do we do that in a nuclear reactor? Here we've got uranium-235 fuel, and that fuel, those uranium-235 atoms, in order to undergo fission, they need to absorb a slow-moving neutron. Now, the neutrons that get released from a fission reaction tend to be moving very fast, have lots of energy, and these high-speed neutrons don't tend to get absorbed by uranium-235 nuclei. Okay, so what do? We have to slow those neutrons down. So in the reactor core, okay, we've got the fuel rods made out of uranium-235. We've got rods or casings of a different material called graphite. And this graphite, we call it a moderator, because what it does is it slows down the neutrons, then turns them from high speed into low speed neutrons, and that increases the chances that they'll go on to do more fission reactions, to cause more fission reactions. Now, to control the output of the reactor, we have these rods that we can raise or we can lower, called control rods. These are made of the very exciting element boron. It's a chemistry joke there. Right, stop laughing. If you need to have a chuckle, pause the video. So the control rods are made of boron, and boron is able to absorb excess neutrons and lock them away. So the control rods, if they're fully inserted into the reactor, they'll absorb lots of neutrons, and the chain reaction will slow down, maybe even stop. If we lift the control rods out of the reactor, and so they're not absorbing many neutrons, then the chain reaction will speed up, or more heat will be produced, and then finally the heat that's produced is carried away by water to turn it into steam, to turn a turbine, to drive a generator in the power station, like we studied before. And around the whole thing we have lots of concrete shielding to absorb the radiation that's released, to absorb the neutrons, any neutrons that escape, and also to keep under control the daughter nuclei, which tend to be radioactive unstable nuclei. So the radiation that's released is absorbed by the shielding, the concrete shielding around the reactor. So if we don't control nuclear reaction, the chain reactions, what happens? This is the Chernobyl power plant accident. The reactor number 4 literally exploded because they removed the control rods, committed a series of mistakes whilst running tests, and caused the reactor to overheat. The reactor overheated so much that the water in the reactor turned into steam. The pressure got so high that it blew the reactor. The reactor blew apart. The lid of the reactor was thrown up into the air and then fell back and chopped the reactor vessel back almost in half. Enormous amount of radiation was released into the environment, but not just radiation, but contamination. Lots of unstable radioactive isotopes were released into the environment, so a lot of contamination. And this is the remains of the building of reactor 4, which has now got a sarcophagus constructed over the top of it to contain all of this contamination. We do use uncontrolled chain reactions in nuclear weapons. For this to happen, we need a certain amount of uranium. This is what we call the critical mass. Once we've got a critical mass, then the chain reaction will increase exponentially. It will happen more and more and more and more until the energy released causes an explosion. So this is a fat man and little boy. So little boy was dropped on, the uranium bomb was dropped on Hiroshima, that was a smaller one. And then Nagasaki had a different type of bomb dropped on it, again a nuclear weapon. And just a few 4-ton uranium bomb, which just really has a few kilos of uranium, has the same explosive power as 20,000 tons of high explosive. Okay, so you've got a Google Doc with a few tables to complete. Okay, and we'll just finish off by looking at fusion reactions, which is what happens in stars.